Imagine pulling into a charging station, plugging in your electric car, grabbing a fast food coffee, and walking back to find your vehicle loaded with enough power to drive from New York to Los Angeles without stopping once. For over a decade, traditional automakers assured the public that such a reality was decades away, bound by the unyielding laws of chemistry and thermodynamics. But that narrative completely collapsed overnight when Elon Musk stepped onto a sunlit stage at a surprise Tesla event and announced a breakthrough that sent shockwaves straight through Detroit, Tokyo, and Beijing. Tesla had unveiled a new battery architecture capable of delivering a mind-boggling 2,000-mile range on a single charge, alongside an astounding 4-minute fast charge time. The announcement did not just raise the bar for electric transportation. It obliterated the entire playing field, leaving legacy car companies and oil cartels staring into an abyss of immediate obsolescence. Wall Street trading desks went into absolute chaos as analysts scrambled to understand how Tesla accomplished what elite materials scientists insisted was impossible. But as the initial wave of euphoria settled across the internet, big questions began to surface regarding how this tech actually works and whether it is truly ready for mass production. And what revealed itself under the hood proved far more complex than anyone could have anticipated. For years, the EV industry was locked in a bitter struggle against the fundamental limitations of traditional lithium-ion cells. Standard electric vehicles rely on liquid electrolytes, where lithium ions slosh back and forth between a graphite anode and a nickel-manganese cobalt cathode. While effective, this chemistry suffers from severe energy density ceilings, high thermal sensitivity, and slow charging rates caused by heat buildup and lithium plating. Tesla's new power cell completely abandons these classic constraints by introducing a stabilized solid-state polymer ceramic matrix integrated with a nanostructured silicon anode. By replacing liquid fluid with a dense solid medium, Tesla managed to fit nearly 4 times the energy density into a pack that weighs less than the current Model S battery. Furthermore, silicon can hold 10 times more lithium ions than traditional graphite, but historical attempts to use it caused the material to swell up and crumble after only a few hundred cycles. Tesla solved this structural decay by wrapping microscopic silicon particles in an elastic graphene framework that expands and contracts naturally without degrading. The result is a pack so dense that range anxiety is killed off entirely in a single stroke. But packing that much energy into a tiny space created an entirely new engineering nightmare that almost destroyed the project before it ever saw the light of day. To achieve a full charge in 4 minutes, a battery must accept an unprecedented torrent of electrical energy without overheating or melting its internal components. Traditional fast chargers cap out at around 250 kilowatts, taking roughly 20 to 30 minutes to push an EV battery to 80%. Pushing 2,000 miles worth of power into a vehicle in 4 minutes requires charging speeds exceeding 1.2 megawatts, a massive power flow typically reserved for heavy locomotive trains or industrial power grids. To prevent the battery from violently overheating under this intense current, Tesla developed a direct immersion cryogenic cooling system using a non-conductive synthetic fluid that circulates directly around every individual cell. This liquid absorbs heat instantly, at the atomic level, keeping the solid-state chemistry perfectly stabilized, even as megawatt-level energy surges into the chassis. Engine components that would normally degrade under high heat remain completely cool to the touch throughout the entire process. The math behind it seemed almost unreal to veteran automotive engineers who had spent their entire careers claiming solid-state batteries could never handle high-current rapid charging without catching fire or forming microfractures inside the solid electrolyte. But Tesla didn't stop at solving the chemistry and thermal challenges, because manufacturing millions of these cells posed an even bigger hurdle. The real secret behind this battery shift lies in how the cells are built inside Tesla's massive gigafactories. Traditional battery production requires massive, energy-inefficient baking ovens that take up miles of factory floor space to dry chemical slurries applied to copper and aluminum foils. This legacy wet coating method is notoriously slow, insanely expensive, and responsible for massive toxic solvent emissions. Tesla bypassed this roadblock by perfecting the dry electrode coating process, a technology originally acquired from Maxwell Technologies years ago that took almost a decade of continuous engineering torture to master. By pressing dry chemical powders directly into ultra-dense metallic sheets using giant high-pressure rollers, Tesla completely eliminated wet solvents, toxic chemicals, and giant drying ovens from the production pipeline. This manufacturing shortcut slashes battery production costs by nearly 45%, while reducing the physical footprint of the factory by over half. Suddenly, the dream of a cheap, hyper-efficient, 2,000-mile electric car transformed from a theoretical science experiment into a terrifying commercial reality for every other automaker on planet Earth. And when news of this manufacturing efficiency leaked out to rival boardrooms, absolute panic broke out across the globe. In Tokyo and Detroit, executive teams called emergency board meetings to assess the damage to their long-term business models. For years, companies like Toyota had bet heavily on hybrid vehicles and slow-burning solid-state research programs, repeatedly assuring shareholders that full battery electric dominance was still decades off. Other legacy giants were already losing thousands of dollars on every single first-generation EV, rolling off their assembly lines due to sky-high battery material costs. Tesla's sudden leap forward effectively turned existing multi-billion-dollar EV factories across the world into instant technological relics before they even reached full capacity. If a consumer can buy an electric car that travels 2,000 miles on a 4-minute charge for less than the price of a standard gas sedan, the economic justification for internal combustion engines completely evaporates overnight. Gas stations, oil refineries, and traditional dealership service bays suddenly face a rapid glide path toward extinction, as consumer demand shifts violently toward zero-maintenance, ultra-long-range electric transport. Yet, while Wall Street hypes the stock to astronomical heights, veteran industry analysts point out that Elon Musk has a long and complicated history of making promises that do not always match up with real-world launch schedules. Critics and short sellers immediately seized on the announcement, reminding the public of past claims that took years longer to deliver than originally advertised. From the full self-driving timeline to the long-delayed Tesla Roadster and Cybertruck production hell, skeptics argue that showing off a functional prototype cell in a laboratory setting is vastly different from mass-producing millions of flawless battery packs annually. Materials experts from elite universities quickly raised red flags concerning the long-term degradation rates of solid ceramic electrolytes subjected to real-world road vibrations, freezing winter temperatures, and intense summer heat waves. If tiny microcracks form inside the solid electrolyte over time, microdendrites could still short out the cell, causing sudden battery pack failure long before the promised million-mile lifespan is reached. Furthermore, charging hundreds of thousands of 2,000-mile EVs at 1 megawatt simultaneously poses a terrifying threat to localized power grids that are already struggling under heavy loads. Power companies would need to invest hundreds of billions of dollars upgrading electrical substations and installing massive localized energy buffer banks to prevent regional blackouts every time multiple drivers plug in for a 4-minute charge. But behind all the engineering debates and grid logistics lies an even larger conflict brewing on the global geopolitical stage. The race to build next-generation batteries has quickly transformed into the ultimate war for global economic and technological dominance. China currently controls over 70% of the world's lithium refining capacity, 85% of synthetic graphite production, and a near monopoly on critical rare earth processing. Tesla's breakthrough shifts the primary raw material focus away from traditional refined graphite and towards abundant silicon and domestically sourced lithium deposits, bypassing traditional supply chain choke points controlled by foreign cartels. By establishing massive raw material processing facilities directly inside North America and securing localized supply chains, Tesla aims to completely insulate its production pipeline from foreign export bans, trade tariffs, and supply disruptions. This move not only threatens foreign battery juggernauts like CATL and BYD, but it also alters the geopolitical balance of energy independence for entire nations. Sovereign wealth funds, heavily invested in oil reserves, are suddenly forced to confront a world where oil demand could drop off a cliff far faster than predicted by energy agencies. Yet, just as the transition appears inevitable, hidden hurdles within Tesla's own manufacturing architecture threaten to slow down the entire revolution. Scaling the dry electrode process to produce billions of individual cells without microscopic defects has proven to be one of the most brutal engineering tasks ever attempted in modern industrial manufacturing. Even a microscopic dust particle, or tiny variation in powder thickness during the high-speed rolling process, can cause a catastrophic short circuit, rendering an entire multi-thousand-dollar pack totally useless. Tesla's engineers are reportedly working around the clock, inside Gigafactory, Texas, attempting to calibrate advanced laser inspection systems and automated artificial intelligence quality control scanners to catch flaws in real time at microsecond speeds. Early yield rates for the new cell were rumored to be far below standard commercial viability, meaning Tesla must burn through vast amounts of cash and scrap material to refine the assembly line before mass production can hit full speed. If Tesla fails to overcome these yield bottlenecks quickly, the promised vehicle delivery dates could easily slip by months or even years, giving desperate rivals a tiny window of opportunity to catch up or engineer counter breakthroughs of their own. But if Tesla hits its yield targets, the implications for everyday society will extend far beyond just passenger cars. Consider the immediate impact on commercial trucking, long-haul logistics, and air travel when energy density hits these high levels. Semi-trucks, which previously required massive, heavy battery packs that significantly cut into cargo capacity, could now haul full freight loads coast to coast, with minimal charging stops that match standard driver rest breaks. Maritime shipping vessels, ferry networks, and even regional commercial aircraft could finally abandon diesel and jet fuel in favor of pure electric propulsion systems, drastically cutting global carbon emissions. The used car market would experience an unprecedented earthquake, as legacy gas vehicles and early-generation short-range EVs lose their resale value overnight, creating an unprecedented wave of technological obsolescence across global transportation networks. Urban planning, highway rest stops, and commercial real estate would undergo a massive redesign to accommodate high-power megawatt charging hubs capable of cycling hundreds of vehicles through in a fraction of the time required today. The shift would represent the single largest energy transition since coal gave way to petroleum in the early 20th century. As the smoke settles around Tesla's astonishing announcement, the automotive landscape stands forever altered, regardless of how fast production ramps up. Elon Musk has once again forced the entire industrial world to play catch-up, challenging fundamental assumptions about physics, chemistry, and manufacturing economics that stood unchallenged for decades. Whether this battery matrix hits public roads next year or faces delays while engineering teams master mass-yield production, the genie is officially out of the bottle. The era of range anxiety, long charging waits, and reliance on fossil fuels for long-distance travel is rapidly drawing to a close, replaced by a high-voltage future moving at terrifying speed. The legacy automotive industry is running out of time, and the world is watching closely to see who survives the coming storm. When you zoom out and analyze the broader trajectory of human transportation, the jump from gas to electricity was always hindered by one single metric: volumetric energy density per kilogram. Gasoline is insanely energy dense, meaning a small tank can carry a heavy metal vehicle for hundreds of miles. For decades, electric vehicle batteries were simply too heavy, too inefficient, and too slow to recharge to truly replace the convenience of liquid fossil fuels. By pushing energy density past the 800 watt-hour per kilogram threshold, Tesla effectively closed the historical gap between liquid petroleum and electrochemical storage. This means that for the first time in modern history, an electric drivetrain is not just an environmentally friendly alternative, but a strictly superior machine in every measurable performance metric. Acceleration, maintenance costs, structural safety, center of gravity, and now range and refueling speed all heavily favor the electric architecture. The ripple effects on global financial markets are already proving to be staggering. Investment funds that spent decades parking billions of dollars in traditional automotive stocks are now frantically reallocating capital into advanced battery technology, raw silicon mining, and grid infrastructure companies. Sovereign wealth funds across the Middle East are accelerating their diversification efforts, fully aware that if petrol demand tanks over the next 15 years, the geopolitical power held by oil-exporting nations will collapse like a house of cards. Meanwhile, technology giants in Silicon Valley and Asia are watching Tesla's vertical integration model with intense anxiety, realizing that Tesla is no longer just an automaker, but an energy ecosystem, AI robotics developer, and battery manufacturing powerhouse rolled into one single dominant force. Inside Tesla's engineering division, the push to master this new architecture has ignited an internal space race of sorts. Reports indicate that teams are working in continuous 24-hour shifts, using supercomputers, running complex digital twin simulations to predict atomic-level battery degradation under extreme stress. Every single variable, from ambient humidity during cell assembly to the exact molecular alignment of the silicon graphene anode, is being analyzed to eliminate any chance of failure in the field. Elon Musk knows that if these batteries roll out with high failure rates or fire hazards, the regulatory backlash could set the company back by a decade and permanently damage public trust in solid-state technology. The pressure on the ground is immense, and the margins for error are practically zero. At the same time, municipal power authorities are trying to figure out how to prepare for the inevitable surge in grid demand. A charging station featuring 20-megawatt capable stalls would draw as much electrical power during peak hours as a small regional airport or an entire suburban shopping mall. To prevent localized power grids from collapsing under the weight of this massive energy draw, Tesla is quietly deploying industrial-scale megapack battery storage installations directly alongside every planned ultra-fast charging location. These massive storage banks charge slowly from the main power grid during off-peak hours, or gather energy directly from local solar microgrids, acting as massive energy reservoirs that discharge instantly into vehicles during 4-minute fast charges. This genius buffer strategy keeps localized power lines from melting while allowing drivers to blast their batteries with insane amounts of power in minutes. Consumer psychology is another critical piece of this puzzle that cannot be overstated. For years, mainstream car buyers held back from buying electric cars due to deep-seated fears of getting stranded in the middle of nowhere during winter storms or long road trips. The idea of standing in a cold, dimly lit parking lot for 40 minutes, waiting for a car to reach 80% charge, kept millions of families locked into gas-powered cars. A vehicle that offers 2,000 miles of range effectively means the average commuter would only need to plug in their car 3 or 4 times per year. The psychological comfort of knowing you can drive across 3 state lines on a whim without ever checking a charging map completely removes the final barrier to mass-market consumer adoption. As other car manufacturers realize they cannot match Tesla's battery chemistry through conventional supply chains, a wave of corporate consolidation is likely on the horizon. Smaller legacy brands that lack the capital to fund multi-billion-dollar battery research and development programs will be forced to merge, seek government bailouts, or license Tesla's proprietary battery technology just to stay solvent. We could soon enter an era where cars built by rival brands are powered entirely by Tesla battery cells, Tesla motors, and Tesla software underneath the bodywork. This level of market dominance would give one company unprecedented control over the world's transportation backbone, transforming Tesla into the ultimate monopoly of the 21st century. The technical reality of the silicon anode also opens up exciting possibilities for next-generation vehicle design. Because the new solid-state battery pack takes up a fraction of the physical volume required by older lithium-ion units, automotive designers are no longer forced to build vehicles around massive, heavy floorboards. This allows for radically improved aerodynamics, lower vehicle profiles, lighter overall weight, and dramatically increased cabin space for passengers and cargo. Future vehicles could look entirely different from anything currently on the road, taking full advantage of the spatial freedom created by dense, ultra-compact energy storage modules. Despite the enormous promises, environmental groups are keeping a watchful eye on how raw materials for these hyperdense cells will be sourced and processed. While eliminating cobalt and heavy graphite reduces reliance on controversial overseas mining operations, scaling up domestic lithium extraction and ultra-pure silicon refining carries its own environmental footprint. Tesla claims its closed-loop recycling program will allow over 99% of raw materials from old battery packs to be recovered and reused in new vehicles, creating a truly circular supply chain that minimizes the need for continuous raw material mining over time. If successful, this circular economic model could set a new global benchmark for sustainable heavy industrial manufacturing. Every major industrial revolution in human history was defined by a fundamental upgrade in energy storage and delivery. The shift from wood to coal enabled the steam engine. The refinement of oil unlocked the internal combustion engine and aviation, and the master of nuclear power transformed global electricity grids. Tesla's new solid-state battery milestone is not just an incremental improvement to an existing car part. It is the next logical step in humanity's mastery over energy storage density. The implications will ripple through society for generations to come, altering where we live, how we travel, and how we interact with the physical world around us. As we look toward the horizon, one thing remains undeniably clear. The transition to a fully electrified, ultra-efficient world is no longer a distant theoretical dream reserved for future generations. It is happening right now, accelerated by relentless engineering, terrifying economic incentives, and an unyielding drive to break through every physical barrier standing in the way. Whether legacy automakers adapt in time or fade away into the history books, the journey toward a zero-emission, hyper-connected transportation grid has reached an absolute point of no return. The race is officially on, and the world will never be the same again.